In this unit, we're moving on to our third major specification of system operation, which is our steady state error. So of course, we've already taken a look at our transient response, so how does our system behave over time? We've taken a look at our stability in the previous unit, which we said was the most important characteristic of our system. And now we're going to be looking at our steady state error, which, as the name implies, is going to be what type of error do we have as our time is going towards infinity or as that natural response decays away. So let's start just by defining our steady state error, and then we're going to talk about some common test inputs we're going to look at. So oftentimes I'm going to abbreviate steady state error as just SS error, just so I don't have to write out the steady state each time. And so what our steady state error is it's just going to be the difference between our input and output as time goes to infinity. So this is our difference between our input and our output as t is going towards infinity. And so one thing to note, so of course that's important there that our t is going to infinity, but another thing to note here is that this is for a given test input. And so we'll talk about this in detail a lot later in some later videos, but for now let's go ahead and talk about some of the common test input signals that we're going to be using. So test inputs, which are commonly used. And so which one we're using depends on our system, what we're trying to sort of figure out about our steady state error. So the one that we're familiar with already is our step input. And so this can be a unit step or it can be modified by some gain. And typically this is going to be used for a position control system. So, of course, our example that we sort of keep revisiting throughout these lecture notes of our elevator would be a position control system, right? We're telling the elevator, our metal box, essentially what position to go to when we press that button, which is the input. And so, in this case, a step input is going to correspond to a constant position. So if we give a position system a step input, that's saying go to this position and stay there. And so another example to sort of relate to some of these later examples with our other test signals is we could talk about a geostationary satellite. So a geostationary satellite is essentially just rotating in space such that it's above the same point on the Earth as it's rotating. So it's essentially keeping the same position relative to the Earth. So constant position, we would input a unit step response, or a step input, not necessarily a unit. So of course that's going to be u of t is just equal to 1 for a unit step response. Again, we can, as we're going to see later, we can scale the magnitude of that. And so if we take the Laplace transform, because we can kind of anticipate we're going to be working in our frequency domain, we get that our u of s is equal to 1 over s. And again, any gain factor is just going to show up as, so if we have k here for t greater than 0, then this is just going to become a k here in the numerator as well. The second common input that we're going to look at is a ramp input. And so our ramp input is going to be relevant for velocity control systems. And so for velocity control systems, this is going to correspond to a constant velocity. And so an example of this to sort of relate to that geostationary satellite for our position control would be a satellite that has a constant velocity relative to Earth's rotation. So satellite with some constant velocity. And then let's just say with respect to Earth's rotation. Okay, and so in this case, our input signal would be r of t, which is our ramp. And so the unit ramp would be just t. Of course, we could scale that. Same way we could scale our step input. And so we can take the Laplace transform of that, and we can say that's going to give us r of s, which is going to be 1 over s squared. Again, any scaling factor is just going to show up in the numerator there. So the third type of common input we're going to look at is our parabolic input. So we could have a parabola. And so this is going to correspond to constant acceleration systems, as you might have guessed. And so an example of this sort of related to our satellites would be a missile or a rocket. So let's do this. So this would correspond to a missile or a rocket, something that's accelerating constantly after launch. And again, there are, of course, certain types of missiles which aren't constantly accelerating throughout their entire flight path, but we're sort of modeling just that initial acceleration from not moving to moving. And so in this case, for our parabola, sort of our parabolic input, I should say, our sort of basic unit parabola is going to be 1/2 times t squared. And so if we take the Laplace transform of that, we see that's going to give us an RS, which is equal to 1 over s cubed. So it's important to note that this 1/2 is sort of our standard unit parabolic input in our time domain. And so that 1/2 corresponds to having a unity numerator in our frequency domain. So again, we can adjust this by some gain, and that's going to show up in the numerator in our frequency domain. So these are our 3 common inputs that we're going to see throughout the rest of this unit. One very important thing to note is that our system has to be stable for any discussion of steady state error to be relevant. So our system must be stable for our steady state error to be relevant. And so what we're going to do as we're working through examples or we're looking at problems in this chapter is we're going to assume stability, and we're just going to sort of focus on the steady state error part of it. But it's very important to keep in mind that if a system isn't stable, then nothing we are doing with steady state error makes sense. So in practice, it's very important as a first step to always check for system stability. From there, once we determine the system stable, we can move on to doing our steady state error analysis.